Welcome back. I'm going to show you in this video how to do mole-to-mole calculations using balanced chemical equations. But let's make sure we understand what's happening during a chemical equation. So in my example here, we're going to say that we're going to take some sodium metal and chlorine gas and make some sodium chloride. So I'm going to count here, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moles of sodium. And over here, chlorine's diatomic, I have 1, 2, 3, 4, 5 moles of chlorine gas. Now, when they react, we're going to form NaCl. So that's one sodium and one chlorine getting together. Well, that leaves behind another chlorine that will mix with another sodium. So you can see I'm starting to make sodium chloride. Now, as long as I still have reactants, the sodium and chlorine left, it will continue to react. So I'll have more sodium and chlorine, more chlorine with more sodium combining, and I've made more sodium chloride. I've now made 4 moles of salt. And I can continue this, taking away my sodium and chlorine and more sodium, and I'm going to continue and continue until at which time I run out of one of or both of the materials. Now, in the example I'm showing you here, we are doing what's called ideal stoichiometry. All of the sodium, all of the chlorine, all of my reactants have been consumed and used. And I've produced 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sodium chlorine molecules. Now, that's what's happening in this reaction. Now I can take those coefficients, the 10, the 5, the 10, and put them up here, but really I want to reduce it to lowest terms. So 10, 5, and 10 reduce to 2, 1, and 2. So really what we're looking at here is a reaction where 2 sodiums combine with 1 chlorine to make 2 sodium chloride. That's the minimum recipe. And then I can scale it up or bring it down to whatever I need. So much like if I were to bake some cookies, maybe I want to make some chocolate chip cookies. That sounds good to me. Well, this recipe says it makes 5 dozen cookies. So let's assume, though, I have 5 eggs and I have all the other ingredients. And I notice it only takes 2 eggs to make 5 dozen. So how many cookies could I make? Well, we could set this up. And here's what it might look like. How many cookies? Always, what are you looking for equal to what do you have, or what do you know? 5 eggs. Now, I'm looking for a conversion, and the recipe is that. What it says is 2 eggs make 5 dozen cookies. That is my relationship. So every 2 eggs make 5 dozen cookies. So eggs cancel. So 5 times 5 is 25 divided by 12. I could make, or 25 divided by 2, 12 and a half. I can make 12.5 dozen cookies. Okay? And that's how I would solve the question. Okay? Now, this slide I got from another teacher, and she does it slightly different. 5 eggs, still use the same conversion. 2 eggs make a dozen, making sure eggs go on the bottom, 5 dozen on the top, and eggs cancel, and you get the 12.5 dozen cookies. Okay? The only difference is when I solve it, I use full parentheses, and I always set what I'm looking for first, and then set what I'm given to, set it equal to. And of course, that would be 150 cookies if we're really answering the question, how many cookies, right? All right. So a chemical equation is nothing more than a recipe of how we make something. Okay? So let's try this. When we start to deal with math, this is all called stoichiometry, the mass relationships or any kind of math relationships between substances in a chemical reaction. And it's all based on the mole ratio. So for right now, we're going to pretty much stick with just mole calculations, but in our next unit, we'll deal with moles and molecules and liters of gas and other things as well. Now, in this equation where I'm burning magnesium with oxygen to form magnesium oxide, I get what's called a stoichiometric ratio. it says for every 2 parts magnesium, I will need 1 part of oxygen. So there's a 2-to-1 stoichiometric coefficient. Now, this does not say 2 grams of magnesium plus 1 gram of oxygen will equal 2 grams of magnesium oxide. No, this is a mole ratio, not a mass ratio. So it says 2 moles of magnesium will react with 1 mole of oxygen to produce 2 moles of magnesium oxide. And we'll spend some time on that, making sure we understand that difference. Now, in an earlier lesson, we talked about 1 mole of something equals the molar mass. 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd. And 1 mole of something that is a gas at what's called standard temperature and pressure would have a volume of 22.4 liters. And standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. We tend to use this conversion when we get to the gas laws unit. We don't always introduce it yet. And this is another teacher's version of the mole island diagram. Notice that mole is in the center, and from moles you can get mass if you go to the left, you can get liters of gas if you go up, you can get particles if you go to the right. So moles is really the center of all of this. Alright, now what we want to do, and we haven't introduced molarity at the bottom, that's why I didn't comment on it. What we want to do is only focus on the mole to the mole ratio within an equation. We're not even going to worry about any of these other little directions at this point. Okay, so let's try this problem here. So it says how many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? Well, what we know is we're starting with potassium chlorate, KClO3. And it says it must decompose. Now remember, a decomposition is an AB goes to A plus B. So we know one of the products it says must be oxygen, O2. Well, what does that leave me? It looks like it leaves me with a KClO, but that's not what we're going to get. Instead, we're only going to get KCl. K is 1 plus, Cl is 1 minus. And I know what you're saying. You're saying, well, this doesn't look like it's going to balance. Well, that's what we have to do next, is balance it, right? So, if we would have looked at the raw equation, KClO3 goes to KCl plus O2, we would have noticed we have 3 oxygens on the product side, or on the reactant side, and 2 on the product. The number 2 and 3 have in common is 6. So that means we put a coefficient 3 here and a 2 here to get 6 oxygens. That then gives me 2 potassium and 2 chlorides on the reactant side, and I have only 1 on the product side. So I add that last coefficient 2. At this point, now we have a balanced equation. Now we can answer the question. So it says, how many moles of KClO3? So what I'm going to write under here, under the KClO3, is X moles. I will tend to write that X moles under there. And we know that we're going to produce 9 moles of oxygen. So I'm going to write 9 moles under the oxygen. Next, what we're going to do is set up a conversion. So we know we have 9 moles of oxygen. I will always set mine up. What am I looking for? X moles of KClO3 equal to what am I given? 9 moles of oxygen. Okay. Then I will use, when I do it, a parentheses. It's not really very different than what you see here. Now, I'm looking for a relationship between moles of oxygen and moles of KClO3. Now, if you remember what we said just a moment ago, we said that the coefficients are not gram ratios, but that is the mole ratio that I'm looking for. So what it says is, for every 2 moles of KClO3 that I decompose, I will generate 3 moles of oxygen. So I could set that equal to each other. 2 moles of KClO3 equals 3 moles of oxygen. Don't worry about the KCl. We're only looking at this part of the conversion. So in order to set that up, I want oxygen to cancel, so it goes on the bottom. For every 3 moles of oxygen, I get 2 moles of KClO3. Moles of oxygen cancel unit-wise, like that. And now I get 9 times 2, 18 divided by 3, 6 moles of KClO3. That's how we can introduce the mole idea to these equations and start to understand the mathematical relationships. Let's do a couple more of these and then we'll probably stop. I'm going to skip, well, let's try this one first. Okay, so I'm giving you a balanced equation to begin with. So it says, how many moles of chlorine gas? So notice what I do next. I write X moles under the chlorine gas are required to react with 5 moles of antimony. Antimony symbol is Sb. So that means I start with 5 moles. Now, I'm going to show you a way that I do not want you to solve the problem because it only works for a mole-to-mole calculation. And unfortunately, we'll do mole to gram, mole to liters, and many other iterations. So I really don't want to see this on your sheet of paper. Sometimes another teacher might show you this method, but it's not going to be useful in the long run. They simply set up a ratio. 2 is to 5 as 3 is to x. So what you would do is say 2 over 5 equal 3 over x. Now to solve that, you cross multiply and divide. 2 times x equals 3 times 5. 2x equals 15. X equals 7.5 moles. Now that works. That is our answer. But again, that's not how I want to see you set it up. I want you to do what I'm doing down here. Set up, what are you looking for? X moles of chlorine equal to what are you given? 5 moles of antimony. Then we're looking for a conversion. And that conversion comes from the coefficients of the balanced chemical equation. 2 moles of antimony will produce or be required to react with 3 moles of chlorine. That's the recipe. I want antimony to cancel, so it goes on the bottom. 2 moles of antimony, 3 moles of chlorine. Now do the math. Well, moles of antimony cancel, like that. 5 times 3, 15 divided by 2, 7.5 moles. Again, somebody's going to show you that you can do these ratios. 2 is to 5 as 3 is to x, cross multiply and divide, and it will work, but again, the caveat is it only works mole to mole. Don't want to see you doing that. Alright, let's try another one. How many moles of antimony chloride are produced from 5 moles of antimony and excess chlorine? So look, I still have 5 moles of antimony, and I'm trying to figure out how much antimony chloride I'm going to make in terms of moles. Now, we're introduced to something new. It says we have an excess of chlorine. Now, anytime we know something's excess, that little x reminds us we can x that out. We don't have to worry about that. If we didn't have enough, that's a completely different problem. That's called a limiting reactant. But at this point, it's excess. So, let's do what we did earlier. Do you remember what we do first? Right. What are we looking for? X moles of SbCl3 equal to what are we given? 5 moles of Sb, the antimony. And of course, I'm looking for a conversion that relates between moles of antimony and moles of antimony chloride, and that is located right there, the coefficients. 2 moles of antimony will produce 2 moles of antimony chloride. I want moles of antimony to cancel, so it goes on the denominator. 2 moles down here of antimony, 2 moles of antimony chloride up here. Moles of antimony cancel like that. Now, the 2's also cancel, don't they? That's just a big way to write 1, 2 over 2. So all that work to find out, I get 5 moles of antimony chloride. Now, some of us could have just looked at that and said, based on the coefficient, because we have a 2, to 2, that's a 1-to-1 ratio. If you start with 5 moles, you're going to make 5 moles. All right, let's try one more. In this question, I want to know, let me erase some of this stuff we have up here. I want to know how many moles of antimony chloride are going to be produced from 7.5 moles of chlorine and excess antimony. So notice what I did. I wrote that information down into the equation at the top. Excess antimony means I can ignore that. So I'm starting with 7.5 moles of chlorine, and I want to know how many moles of antimony chloride. So set it up the way I've shown you. What are you looking for? X moles of antimony chloride equal to, what do you know? 7.5 moles of chlorine. Anytime you're looking for a conversion, mole to mole, you only have to look as far as the balanced coefficients. 3 moles of chlorine will produce 2 moles of antimony chloride. So that's my conversion. I want it set up so moles of chlorine cancel, so it goes in the denominator. The numerator is the 2 moles of antimony chloride. The moles of chlorine cancel, like that. 7.5 times 2 is 15 divided by 3. I get 5 moles of antimony chloride. All right, I hope you're starting to see how this works. Mole-to-mole calculations are pretty simple. You can expect 1 or 2 of these on the test on chemical equations. They were not on your quiz, but they will be on the test. Let's try another one just for fun, right? And again, what you can do is, if you want, you can pause, read the question, try to work it out yourself, and then unpause and make sure you did it correctly. So we want to know how many moles of magnesium oxide, so I'm going to write X moles under the magnesium oxide, are produced from the burning of 10 moles of magnesium. That's my question. Now, I have to assume that I have excess or at least adequate amount of oxygen, because they didn't tell me about that at all in the question. Now, some of you are like, I know the answer, it's 10 moles. Excellent, because you're looking at the coefficients. 2 moles of magnesium produce 2 moles of magnesium oxide. So therefore 10 moles of magnesium should produce 10 moles of magnesium oxide. If you didn't make that connection, well, let's work it out. How many moles of MgO equal 10 moles of Mg? Using the coefficients, 2 moles of Mg produce 2 moles of MgO, making the moles of Mg go in the denominator so that the unit cancels. I get 10 moles, as you told me we were going to get a second ago. Let's try another one. Let's try this. And let me erase this. How many liters of oxygen? You know what? We're not even going to do that one, because right now the only thing I want you to do is mole to mole. So I'm not going to worry about liters on there at all. Now, if we wanted, we could say, well, 1 mole of oxygen is 22.4 liters. Perhaps you remember that conversion. So that if I really wanted to figure out how many liters of oxygen equal 10 moles of magnesium, I could do this as a conversion, and I would get moles of oxygen to be 5 moles. But then I would have to add that last step, that every 1 mole is 22.4 liters, to get my answer there of 112 liters. Now, again, I'm not going to ask you at this point a question like that. I'm going to be sticking with my questions mole to mole at this point. Okay? All right. So I'm going to skip all that. I'm not interested in that. Let's try this one. And maybe we'll make this our last example, since we're at about 20 minutes. I got calcium chloride, and this is obviously a decomposition reaction. When it decomposes, it makes calcium metal and poisonous chlorine gas. So, how many moles of calcium metal and chlorine gas are produced from the decomposition of 8 moles of calcium chloride? So, initially, we're going to do this in 2 steps. We're going to figure out how many moles of calcium are made from 8 moles of calcium chloride. Now, be careful, you have to have a balanced chemical equation to make this work. Now, if you look at it, you're like, well, it is balanced. Yes, it is. And therefore, for every 1 calcium chloride, you produce 1 calcium. So I think you already know the answer is going to be 8 moles. But let's go ahead and work it out just for fun. How many moles of calcium is equal to 8 moles of calcium chloride? Using the coefficient, 1 mole of calcium chloride, 1 mole of calcium, I'm going to put that in. The moles of calcium chloride cancel, and I get my answer, 8 moles of calcium. Now, the second part of the question, and now we can do that, says how many moles of chlorine gas are produced from the decomposition of 8 moles of calcium chloride. Well, look, it's a 1-to-1 ratio again. So the answer is going to be 8 moles, but we can set it up. How many moles of chlorine equal 8 moles of calcium chloride? The coefficients are where I get the mole ratio. Anytime you go from one substance to another, the conversion factor is the mole ratio. So 1 mole of calcium chloride, 1 mole of calcium, moles of calcium chloride cancel like that, and I'm left with 8 moles of chlorine. Okay? All right. I was going to go through this, but I'll save that. We can chat about that one in class where it's a little bit more in depth on that. So I hope this helped you understand how we do mole-to-mole conversions using the balance coefficients from a chemical equation. Thanks for paying attention. Bye-bye.